Welcome to the Deep Dive, the show where we sift through the noise, grab a stack of information, and really try to pull out those important nuggets of knowledge just for you. Today, we're not just diving deep, we're actually taking a chronological plunge way back to a really pivotal, almost magical time in the history of artificial intelligence, the 1970s and 1980s. This was such a fascinating period, a time when computers started moving beyond just, crunching numbers and doing basic math. They were daring to promise something much, much bigger, replicating human intelligence itself.
That's right.
It was really the dawn of what we now kind of affectionately call expert systems, a whole new type of software designed not just to process data, but to capture and actually use specialized human expertise.
Yeah, the mission back then was incredibly ambitious, but also very focused. It was about taking all that messy, complex human knowledge, stuff from scientific papers, research notes, maybe even just an expert's own scribbled thoughts, and somehow encoding that into a machine.
Right. The aim wasn't general intelligence like you see in the movies that can talk about anything. No, it was about building systems that could reason, analyze, make decisions, but only within a very specific, narrow area. Highly specialized.
Exactly. So our deep dive today isn't just, a history lesson. It's almost like a detective story. We're going to trace how these expert systems rose up, how they actually worked this idea of encoding expertise into rules, and why they became AI's very first big commercial success story. That really sparked a wave of optimism.
It really did.
But crucially, we also need to look at how their limitations, the things they couldn't do, hinted at the big challenges, maybe even those AI winters that were still down the road for the field. It's a story of incredible promise, applications that felt like sci-fi, but also unexpected hurdles that made everyone rethink what AI really is. Okay, so let's try and picture this time. The very idea of a machine making complex decisions that usually needed a human expert, well, it felt almost like magic, didn't it? Straight out of science fiction. It really did. And before these expert systems really took off, the public's imagination was already being captured, sometimes maybe even a little startled, by earlier AI attempts that gave a glimpse, even if it was a bit superficial, of what might be coming.
Yeah, and what's interesting is how they defined AI back then.
Right. Even in those early days, the definition of artificial intelligence was pretty comprehensive. It was seen as the ability of an entity to perform actions towards its objectives, needing things like perception, decision-making, learning, and even language understanding.
So quite broad already.
Yeah, surprisingly so. But while today we talk a lot about learning from data, these early efforts, especially the expert systems, were laser-focused on that decision-making part by formalizing existing knowledge. They weren't trying to get machines to learn on their own. They were trying to bottle up human judgment.
And before they got to those really practical, high-value expert systems, there were these fascinating early programs that created this, illusion of intelligence. They really grabbed people. Let's talk about ELIZA first.
ELIZA. Developed by Joseph Weissenbaum at MIT back in the mid-60s.
Right. It didn't actually understand anything, did it? It was more like a clever trick.
Exactly. It used, simple tricks, mostly pattern matching. It would find keywords in what you typed and then kind of reflect it back as a question. Like you'd say, I'm feeling sad. And it might say, why do you say you're feeling sad?
Yeah, very simple mirroring.
But the genius, or maybe the unsettling part, was how it exploited the human tendency to project meaning and emotions onto machines. We're just so wired to find connection that even that basic mirroring felt, almost like empathy to some people.
It really says more about us than the machine in a way.
Absolutely. Weissenbaum himself was reportedly quite disturbed by how readily people, even his own secretary, seemed to confide in ELIZA. It showed how easily we anthropomorphize.
And then came Perry, which took it a step further, maybe a darker step.
Yeah, Perry was developed by Kenneth Colby, a Stanford psychiatrist and computer scientist. It was, let's say, a more sophisticated and, frankly, slightly more unnerving version of ELIZA. Well, instead of just mirroring, Perry simulated a specific persona, a paranoid schizophrenic patient. It didn't just use keyword matching. It had a more complex model trying to incorporate things like emotions, beliefs, motivations, and memory. It had this internal model of its beliefs that made its responses more consistent, albeit paranoid.
Wow. Okay, so it was trying to be more consistent in its delusion?
Kind of, yeah.
Yeah.
And the truly remarkable thing, maybe a bit chilling, is that Perry was apparently convincing enough that it fooled some psychiatrists who evaluated its transcripts along with those of real patients. They couldn't always tell the difference.
That's incredible. It really highlights how quickly you could create a perception of intelligence, even if the underlying mechanism was still, relatively simple compared to human thought.
It blurred the lines for a moment, definitely. Showed how easily we can be led to believe there's understanding there.
So Eliza and Perry were these fascinating conversational experiments, but the expert systems were really aiming for something different, right? More practical, less about illusion.
Exactly. That was the key shift. While Eliza and Perry were about conversation, maybe exploring the human psyche, expert systems were about tackling specific high-value problems, moving from, let's say, illusion to actual application.
So not trying to chat, but trying to do something useful.
Precisely. The realization was that general, human-like intelligence was maybe too hard, perhaps impossible at the time, but specialized expertise, maybe that could be captured. The focus narrowed dramatically. Solve this specific problem, diagnose this specific disease, configure this specific machine.
So they needed to formally represent that specialized knowledge, like taking a super detailed textbook or maybe an expert's brain and breaking it down into rules a computer could follow.
Exactly. Not just the textbook, but the expert's thought process, trying to capture how the heuristics, the rules of thumb, the decision steps that an expert uses, often without even consciously thinking about it. That was the grand challenge.
Okay, so let's really get into the nuts and bolts here. This is where the serious engineering happened. How did these expert systems actually think or reason? Because like you said, it wasn't about learning from data like today's AI. It was all about explicitly programmed rules, handcrafted almost.
Yeah, handcrafted is a good word for it. The core was knowledge representation, figuring out how to structure human expertise so a machine could actually use it. Took a lot of ingenuity.
Can you give us an example? How would you represent something complex?
Well, let's take a relatively straightforward example first. Imagine trying to automate valuing a used car. You could take something like a used car catalog, such as Kelly's Blue Book.
Okay, yeah. Lots of specific data points.
Right. You might encode facts like a 1973 Dodge van with 50,000 miles, and standard features is worth, say, $575. You do this for maybe 11,000 models or however many are in the book. These become simple, logical sentence facts stored in the system's knowledge base.
Okay, so a big database of facts. How does it use them?
That's where something like a backward chaining theorem prover, such as Prolog, might come in. Prolog was a popular language for this. Think of it like a detective. You ask it a question, like, what's the value of this specific 1973 Dodge van with these features?
Right.
Prolog works backward from that goal. It looks for rules or facts that could help establish the value. It checks the make, the model, the year, the mileage, any exceptions, and tries to logically deduce the answer based on the facts it has. If it needs more info, it might even ask.
So it's like an automated deduction machine following the logical links between facts and rules?
Precisely. A clear example of encoding specific facts and rules and then using logical inference to get answers.
Okay, that makes sense for something like a car catalog. But real expertise, like in medicine or chemistry, it's often fuzzier, right? It's not always simple facts. There are exceptions, nuances, usuallys, and sometimes. How do they handle that ambiguity? The stuff beyond simple if then?
That's a really crucial point. And it's where things got more sophisticated. They needed ways to handle exceptions and uncertainty. This led to the use of non-monotonic logic.
Non-monotonic, what does that mean?
Okay, so in standard logic, monotonic logic, once you prove something is true, adding more information never makes it false. It stays true.
Right. More facts just add up.
But the real world isn't like that. You learn something new, and it might completely change your conclusion. Non-monotonic logic allows for that some conclusions can be invalidated by adding more knowledge. It lets you handle defaults and exceptions gracefully.
So like the classic birds fly example.
Exactly. You might have a default rule. Birds normally fly. But then you add more specific knowledge. Penguins are birds, but penguins don't fly. Or this specific bird has a broken wing, so it doesn't fly right now. Non-monotonic logic provides a formal way to say, use the default rule unless there's a specific exception that overrides it.
Oh, okay. So it builds in the unless clause.
Precisely. A rule might look something like B is normally true if C is true, unless it's abnormal in some specific way. It allowed systems to reason with incomplete information and handle the messy reality where rules often have exceptions. It was a big step beyond simple if-then logic.
That seems essential for anything complex. What about changes over time? If the system performs an action, how does it know what changed and what stayed the same? That seems like another headache.
It absolutely was. And it's related to something called the frame problem. To handle this, they used frame axioms. These are formal statements that explicitly describe the effects of actions, what changes, but also, crucially, what remains the same.
Why is stating what stays the same so important?
Because in pure logic, if you don't explicitly state that something remains true after an action, the system might assume it could have changed. Imagine a robot moving a block. You need a frame axiom to say that moving block A doesn't suddenly change the color of block B or make the table disappear unless the action specifically involves those things.
Got it. Otherwise, the possibilities explode.
Right, so a positive frame axiom might state that if certain conditions are met, a property, like block B is red, remains true after an action, like robot moves block A, is performed. It sounds tedious, but it was vital for modeling dynamic environments and allowing systems to reason about sequences of actions and their consequences. It kept the model of the world consistent.
Okay, so they had facts, they had rules with exceptions using non-monotonic logic, and they had frame axioms to handle changes. With all that machinery, these systems could then actually make decisions, right? Follow a complex chain of reasoning.
Exactly. All this encoded knowledge, the facts, the rules, the heuristics, was fed into an inference engine. You can think of the inference engine as the brain of the expert system. It takes the input data about a specific problem, applies the relevant rules from the knowledge base, and follows the logical chain to arrive at a conclusion or a recommendation.
Like a doctor diagnosing a patient.
Very much like that. The system might follow a path similar to a diagnostic flowchart, asking questions or requiring data input along the way to narrow down possibilities, just like a human expert would. This structured reasoning process allowed them to tackle really complex problems, like medical diagnoses or chemical analysis, with impressive consistency.
And consistency was key, right? They didn't have off days.
Never. They always follow the rules exactly as programmed. That was a huge part of their value.
You know, thinking about breaking down complex human phenomena into rules, there's another really interesting example, though maybe not a computer system itself initially. The facial action coding system, or FACS.
Ah, yes, Ekman and Friesen's work from 1978.
Right. They identified something like 40 distinct muscle contractions in the face, tiny movements, a brow furrow, a lip corner pull, and called them action units.
A way to objectively measure facial expressions.
Exactly. But using it manually was apparently very labor-intensive. You needed tons of training to reliably spot these subtle action units and decode the emotion being expressed.
It's incredibly detailed work.
But if you think about it, FACS is a perfect analogy for an expert system's knowledge base. It's taking something incredibly complex and nuanced human facial expressions and breaking it down into a structured, rule-like system. You combine certain action units, you get a specific expression linked to an emotion.
That's a great comparison. It's exactly the kind of detailed, specialized knowledge that, in principle, you could encode into an early AI. You could feed it video, have it identify the action units, and infer the emotion based on the FACS rules. It illustrates that process of codifying human expertise, even for something as seemingly intuitive as reading faces.
So with these sophisticated methods for encoding and using knowledge, it's really no wonder that expert systems became the first big commercial success story for AI. This wasn't just theory anymore. This was AI leaving the lab and actually delivering tangible value in business and industry. A huge moment.
Absolutely huge. They excelled at these specialized problem-solving tasks where human expertise was deep, valuable, but also maybe scarce or expensive.
Like the medical example you mentioned earlier.
Exactly. MyCIN, developed at Stanford in the 70s, is a classic. It was designed to diagnose bacterial blood infections and recommend antibiotic treatments. That's a complex task involving reasoning about different bacteria, patient symptoms, lab results, drug interactions.
High stakes, too.
Very high stakes. MyCIN had hundreds of rules, like if the bacteria is gram-positive, it looks like coccus under the microscope and it grows in chains, then there's suggestive evidence with a certainty factor of, say, 0.7 that it's streptococcus. It could provide advice often on par with human infectious disease experts.
That's amazing. Basically making expert medical knowledge more accessible.
Precisely. And it wasn't just medicine. Another pioneering system even earlier was Dendril, also from Stanford, started in the late 60s.
What did Dendril do?
It tackled organic chemistry. Its job was to deduce the molecular structure of unknown chemical compounds based on data from a mass spectrometer. You feed it this complex spectral data, basically a graph, and it would suggest possible arrangements of atoms.
Something that would normally take a highly trained chemist?
Years of training. Dendril used a huge knowledge base of chemical rules and heuristics. It used a method called generate and test. It would generate plausible molecular structures and then check if they fit the observed spectral data. It didn't just help chemists. Arguably, it contributed to actual scientific discoveries. These were powerful tools solving real scientific problems.
So not just assisting, but potentially accelerating science. What about in, say, industry? Were there big business
Oh,
applications?
definitely. Perhaps the most famous commercial success story was R1, which was later renamed XCon for Expert Configurer. This was developed at Carnegie Mellon and used by Digital Equipment Corporation, or DEC, starting around 1980.
DEC, they made the VX computers, right? Big machines.
Exactly. And those VAX computers were highly customizable. Customers could order them with all sorts of different components, peripherals, memory options, cabling. Configuring each unique order correctly was a massive headache for the human sales and engineering teams.
I can imagine. Lots of room for error.
Tons of errors. Mistakes meant delays, wrong parts shipped, frustrated customers, huge costs. XCon encoded all the rules, thousands of them, that human experts use to correctly configure a VAX system. You'd feed it a customer's order, and it would figure out all the necessary components, check compatibility, determine the right cables, layout, power requirements, everything.
Automating that whole complex configuration process.
Right. And the impact was enormous. Within just a few years, DEC estimated that XCon was saving them something like $25 million a year.
25 million back in the early 80s. That's
Yeah.
staggering.
Astronomical. It dramatically reduced errors, sped up the order delivery cycle, and freed up human experts. It wasn't just about efficiency. It was like consistency and cost savings. A clear demonstration of AI delivering massive value right in the heart of a major corporation.
Wow. So with successes like MyMyCine, Dendrol, and especially Exxon saving millions, the economic impact must have felt really significant. It must have changed how people viewed AI's potential.
It absolutely did. It was a powerful proof point. This first wave showed that AI, even in these earlier rule-based forms, will unambiguously enhance productivity, as some economists might put it now. It proved AI could move out of the realm of academic curiosity and government research grants and become a genuine engine for economic benefit.
From theory to profit.
Exactly. Even if it was localized to specific tasks and industries, it was a crucial demonstration. It fueled a huge amount of investment and excitement. People started talking about an AI spring.
And with that kind of success, the economic validation, the optimism must have been sky high, right? It must have felt like automating more and more human intelligence was just a matter of time.
The optimism was immense. There was a feeling that we'd cracked it, that we just needed to keep encoding more knowledge, build more expert systems, and soon machines could handle any specialized task.
Yeah.
The future looked incredibly bright, perhaps unrealistically so in hindsight. It felt like AI was finally on an unstoppable path.
But, well, as often happens with these huge technological leaps, that soaring optimism eventually collided with some pretty hard realities. We need to shift gears now and talk about the limitations, the things that ultimately stalled that expert systems boom and foreshadowed those periods of disillusionment, the AI winters that the field would face later. And these challenges often popped up when these very specialized systems tried to step even slightly outside their narrow comfort zones, right? When they encountered the messiness of the real world.
That's exactly it. And arguably, the biggest, most fundamental hurdle they hit was what's often called the common sense problem.
Common sense. Seems simple enough. Or maybe not.
Well, that's the thing. It seems simple to us because we live and breathe it, but trying to explicitly capture it in rules turned out to be monumentally difficult, maybe even impossible. As researchers dug deeper, they found that human knowledge just doesn't seem to lend itself to being codified exclusively in a formal logical language. It is too self-contradictory, too context-sensitive, and has too many corner cases.
Too messy for logic, essentially.
Way too messy. Trying to write down every single implicit assumption, every possible exception, every contextual nuance that informs our everyday understanding, it's like trying to count grains of sand.
Can you give us some concrete examples? Where did these systems just fall flat on common sense?
Oh, the examples are often quite telling, sometimes almost funny. Think about basic facts, like, of course cats have tails. Simple enough, right?
Yeah.
But then someone points out, except for the Manx cat native to the Isle of Man, a breed of proudly tailless cat. Okay, add an exception rule.
Right.
Or, of course, crows fly. Well, unless they have their wings clipped or are dead, or maybe they're a baby crow that hasn't learned yet, the exceptions pile up immediately.
It never ends.
Exactly. Or consider, of course, elephants don't fly. Seems pretty solid. But then what about if you put one in a huge Antonov cargo plane? Does that count? And, what about Dumbo? It sounds silly, But these examples powerfully illustrate why trying to anticipate and encode every possible qualification and context for even simple common-sense knowledge makes rule-based systems incredibly brittle. They lack the flexible, context-aware reasoning we use constantly.
It sounds like you'd just be endlessly chasing exceptions, adding rule after rule after rule.
Which led directly to this idea of the infinite rabbit hole. The whole attempt to catalog all human knowledge by hand is a near infinite rabbit hole, an endless task whose scope grows by virtue of its own pursuit. Every time you think you've covered something, you realize 5 more situations you didn't account for.
And this became known as the
knowledge acquisition bottleneck. It wasn't just hard to write the rules, it was incredibly difficult, sometimes impossible, to even get the knowledge out of human experts in a complete formal way. So much of expertise is intuitive, subconscious, learned through experience, not explicitly articulated as rules.
like asking a grandmaster chess player to write down every reason for every move they make.
Exactly. They often just know based on pattern recognition and intuition built over years. Trying to force that into explicit if-then rules often loses the essence. This bottleneck was a fundamental barrier.
Beyond just common sense facts, there was also the issue of understanding context and maybe intent in communication, right? Even in simplified worlds.
Yes, that was another major challenge. A famous example comes from SHRDLU, that early natural language system developed by Terry Winograd that worked in a simple blocks world.
Right, it could move virtual blocks around.
It was impressive for its time. It could understand commands like pick up the red block and answer questions like what is the cube supported by? But in one well-known interaction, when told to grasp the pyramid, and there might have been multiple pyramids on the screen, SHRDLU replied, I don't understand which pyramid you mean.
It couldn't figure out the context or maybe make a reasonable assumption.
Exactly. It lacked the ability to disambiguate based on the ongoing dialogue or the visual scene in the way a human would effortlessly. It highlighted this deep difficulty AI had in grasping context, shared understanding, and implicit meaning, even in a highly constrained environment. We just fill in those gaps automatically. Machines struggled immensely.
And alongside these practical roadblocks, there was also some important theoretical work around that time that pointed out fundamental limits in some of the underlying AI models, wasn't there?
Yes, absolutely. This ties into the work of Marvin Minsky and Seymour Papert, particularly their 1969 book, Perceptrons.
What was their key finding?
They presented a mathematical proof showing a critical limitation of simple, single-layer neural networks, the perceptrons of the day. They proved that a single-layer network can only classify datasets which are linearly separable.
Linearly separable, meaning?
Imagine plotting data points on a graph. If you can draw a single straight line to perfectly separate one class of points from another, then it's linearly separable, and a simple perceptron could learn that boundary.
Okay.
But many real-world problems aren't like that. The classic example is the XOR problem. Think of a checkerboard pattern. You can't draw one straight line to separate the black squares from the white squares. Minsky and Papert showed that single-layer perceptrons fundamentally couldn't solve problems like XOR.
So these simple networks were mathematically limited in the kinds of patterns they could learn.
Exactly. Now, their work was sometimes overinterpreted as saying all neural networks were fatally flawed, which wasn't quite true, but it definitely contributed to a slowdown in neural network research for quite a while, part of an earlier AI winter. But more broadly, it highlighted that intelligence wasn't just about connecting simple units. You needed more complex architectures to handle complex, nonlinear relationships found in the real world.
And this related back to the expert systems problem, too.
In a way, yes. It underscored that you needed more than just simple rules or simple networks. Minsky and Papert argued you needed theories of problem domains and not simply a theory of perceptrons. This really mirrors the expert system's big limitation, domain specificity.
Right. Great at one thing, useless at everything else.
Precisely. Mike CIN was brilliant for blood infections, but couldn't tell you the time. XCon could configure a VAX, but knew nothing about chemistry. They couldn't generalize, couldn't adapt, couldn't transfer knowledge. Their intelligence was deep in one narrow well, but incredibly brittle outside of it.
So, that initial magic, the ELIZA effect, the promise of XCon, it eventually gave way to this realization of deep limitations. The common sense barrier, the knowledge acquisition bottleneck, the theoretical limits, it showed these systems didn't have true understanding or adaptability.
It was a necessary, if humbling, reality check. It forced the field to confront the immense gap between rule-based expertise and genuine, flexible intelligence. It was clear a different approach would be needed.
Okay, but here's the really fascinating part, I think. The story doesn't just end with disappointment and another AI winter. Those lessons learned from the expert systems era, the failures even, weren't dead ends at all. They were actually crucial stepping stones. The struggles became the fertile ground for completely new ideas.
That's absolutely right. The sheer difficulty, the brute force effort involved in trying to manually codify all human knowledge, rule by rule, exception by exception, it became painfully obvious that this approach probably wouldn't scale to general intelligence. It forced researchers to think differently.
How so? If writing down all the rules was the bottleneck, what was the alternative?
Well, it pushed the field decisively from rules to learning. If you can't tell the machine every single thing it needs to know, maybe you can create systems that can learn from experience, from data,
Right.
much like humans and animals do.
Ah, the birth of modern machine learning in a way.
Exactly. This profound shift towards machine learning, developing algorithms that allow computers to learn patterns and make predictions from data without being explicitly programmed for every task, really gained momentum, partly because of the limitations exposed by expert systems. It laid the groundwork for the neural networks, deep learning, and statistical approaches that are so dominant in AI today. It was a move from programmers teaching the machine rules to the machine learning rules, or patterns, really, from data itself.
From telling to showing, essentially.
The great way to put it, show the machine thousands of examples of cats and let it figure out the patterns rather than trying to write down a perfect logical definition of cat with all its exceptions.
And this whole experience must have also given everyone a renewed appreciation for what humans do so effortlessly, the things the machines found so hard.
Definitely. The struggles of expert systems really highlighted unique human cognitive strengths. Our amazing ability to make analogies or recognize useful similarities in different contexts. Our capacity to reason with incomplete information, to handle ambiguity, to deal with totally unexpected situations, the unknown unknowns, where a rule-based system just grinds to a halt because there's no pre-programmed rule for it.
Right. A doctor facing a completely novel set of symptoms can draw on intuition, analogies, general medical principles. An expert system hits a wall.
Precisely. And recognizing this led to a more nuanced view. Instead of just aiming for full automation to replace humans, the conversation started shifting towards collaboration, towards building systems that could augment human intelligence, AI handling the data crunching and rule following, humans providing the common sense, context, and creative problem solving, playing to each strength.
So we see this clear trajectory. Expert systems focused intensely on encoding prior knowledge, the rules given by humans, but the next wave had to be different.
Yes. The next waves, particularly with the resurgence of neural networks and the rise of deep learning, powered by more data and computing power, shifted the focus heavily towards learning from past experiences. This includes interaction with the environment, vast data sets, user feedback, letting the system learn patterns and build its own internal representations from data, rather than relying solely on human-encoded logic.
So it's a fundamental shift from human-defined symbols and rules to machine-learned statistical patterns.
That's a very good summary of the transition. It wasn't that rules became useless, but the primary mechanism for building intelligent systems shifted dramatically towards learning from data.
It really puts the expert systems era in perspective. It wasn't a failure, not at all. It was this absolutely essential phase that showed us both the incredible power of formalizing knowledge and its profound limits. It revealed just how complex intelligence, especially human intelligence, truly is.
Couldn't agree more. It taught the field invaluable lessons, defined the challenges more clearly, and ultimately pointed the way toward the more powerful, flexible, learning-based AI systems we're developing today. It set the stage perfectly for what came next. Hashtag tag tag outro.
Okay, let's wrap this up. Our deep dive today took us back to the really exciting and ultimately quite challenging era of expert systems in the 70s and 80s. We saw the initial thrill of capturing human expertise in software, the amazing commercial successes like MYCIN and XCon that really felt like AI had arrived.
That first AI boom.
Right. But then we saw the collision with reality, the immense difficulty of encoding common sense, dealing with exceptions, the sheer brittleness of systems built entirely on explicit rules when faced with the messy real world.
And it's so important to remember that those hurdles, those AI winters they sometimes triggered, weren't failures in the end. They were signposts. They forced a much deeper reckoning with what intelligence actually is and how complex it is to replicate. They guided the field away from pure logic and towards the statistical, learning-based approaches that dominate AI now. Every limitation revealed was a lesson learned.
Absolutely. And that leaves us with a final, maybe slightly mind-bending thought for you, our listener. Think about how incredibly hard it was for those pioneering expert systems to handle the seemingly simple exceptions to common sense rules. You know, tailless cats, flightless crows, understanding context.
Stuff we don't even think about.
Exactly. What does that difficulty tell us about the vast ocean of foundational knowledge we swim in every single day without even realizing it? How much of our own understanding, our intuition, our common sense remains implicit, unquantifiable, maybe even fundamentally resistant to being perfectly captured in code, even by today's most powerful AI?
It's a humbling question.
It really is. Something to ponder as you navigate your own world of knowledge, exceptions, and maybe, just maybe, give a little nod to the incredible complexity humming away inside your own head.